Welcome back to the last session of this workshop. So in this session we will have 4 presentations. The first presentation will be delivered by Professor Jeff Naber. He will present on diesel spray injection. And to give a brief introduction, Professor Jeff Naber is a Ronan Elaine Star Professor in Energy Systems in Michigan State University.
Michigan Tech.
Michigan Tech. I'm sorry. His research interests are combustion processes and combustion of hydrogen and hydrogen fueled biofuels including ethanol with production from forest products and application in advanced combustion sciences. I request Professor Naber to deliver his presentation.
Thank you. So I got this job now to convince you that there is a little bit of work left to do in diesel spray characterization, and hopefully we can discuss that and see if I can get at least a couple of you to agree maybe on a perspective that there is some work there to do. And I do appreciate inviting me here. If you're familiar where Michigan Tech is, it's located a little bit further north than some of the other state schools. We're approximately 500 miles north of the Detroit area. If you know where UW-Madison is, we're another 5 hours north of there. We sit on Lake Superior, which is beautiful, but we've already gotten about 2 feet of snow already this year, so we're well on our way for a white Christmas. So with that, I'll go ahead and talk about diesel spray injection. And first I'm going to talk about the application a little bit and where do we stand with current injection systems in a little bit more detail than John did, and really how current diesel engine emissions in both the US and Europe have really impacted the system, and how fuel systems have adapted to enable us to meet the emission standards, but limitations in the fuel system are meaning that we're not operating under optimal conditions currently. And then I'll talk about the state of spray and combustion diagnostics and some parameterization work that's been done at Sandia and some of the work that's already been discussed. I'll talk about a new partnership that John alluded to, is this ECN partnership that's been established by Sandia. I'll talk a little bit about fluids and their impact in the system, and then finally talk about dynamic characteristics and internal structures, which I think are an important area which we need to understand more about in these sprays. So first, what is a diesel injection system? And John had pointed some of this out. There's a single pump that's distributing high pressure fuel to a fuel rail. And then depending on the number of cylinders, there's an injector per cylinder. They're electro-hydraulically controlled. The actuator is typically a solenoid or a piezoelectric crystal. Injection pressures currently are about 2,000 bar, but we expect that to be at 3,000 bar or higher in the near future to continue to improve mixing and to hopefully alleviate some of the concerns with the NOx PM trade-offs. Holes, I had a laser drilled. This is 140 micrometer, but can be down to the size of 80 micrometers. Argon's done a lot of great work in imaging these nozzles with a number of their tools, but you can see here's the seat of the pintle. If you were to see really closely, you can see the nozzles coming here out in the end, and there's a small sac volume. The nozzle holes are laser drilled, but then they're also ground with hydraulic grinding to create specific shapes in here to improve their flow capability. And depending upon the amount or the type and how the laser drilling is done and the amount of this hydro grinding, we can affect some of the shape factors in these nozzles, and that can give us a significant measurable difference in performance in the engine in terms of emissions characteristics. Injection periods can be as short as about 50 microseconds, I should say, with 3 or more pulses typical. 3 is typically the minimum, and I'll show you what that looks like in a second. But I think there's a critical need to understand what the internal effects of internal flows are and how that's driving effects downstream that maybe we don't see in global characteristics of the spray that we'll talk about, spray penetration or cone angle or some of the other global parameters, but are measurable when we go to the engine and make measurable differences in soot emissions. So what I'm going to do is kind of highlight what I think are some of the shortcomings or some of the needs by this little red box in here just to help you track. So where do we stand? And European standards are closely tracking this, but these are US on-road heavy-duty emission standards. And we were able to make the first couple decades or decade and a half reduction in emissions through advancing the fuel system, going from mechanically controlled to electronic control, increasing injection pressures, reducing orifice nozzles, and then through advancement in combustion systems. But starting in, to make the 2004 emission standards, we had to add exhaust gas recirculation and dilution, so it was still primarily an in-cylinder solution. But to make the 2007-2010 standard, we now have complex after-treatment systems that are required for NOx and particulate. So there's a oxidation catalyst that plays additional roles in addition to just oxidizing CO and hydrocarbons. It also turns some NO to NO2 for passive oxidation in the DPF, but there's a particulate filter and an SCR system typically in heavy-duty applications. So although we were very successful in developing fuel systems and combustion control, we weren't able to meet this 90% reduction in particulate and a 90% reduction in NOx, not surprising, with continued development here. There was a big jump between these years. And so now we have to deal with after-treatment systems. But what's happened in this time period is that we've had to move along this NOx-PM trade-off. So if we have higher temperatures, we'll have higher NOx but less particulate. If we have higher dilution, lower temperatures, we'll have lower NOx but higher particulate matter. So what's happened is that we've essentially reduced the combustion temperatures by dilution and retarding combustion. So whereas we would have injection and combustion starting a little bit before top dead center, giving us an optimal combustion phasing, we're now significantly retarded that combustion phasing to enable us to make the NOx emissions. That's directly a penalty in fuel economy. So we have a direct impact of not being able to make emissions through in-cylinder combustion, resulting in a negative impact or reduction in fuel economy. So we're operating with non-optimal phasing or non-optimal combustion systems. And is there a mechanism with which we can improve this? Because if we were to recover combustion phasing, we would make a direct impact on efficiency. You can kind of see this in the way that the fuel system operates to control the engine currently. Here's a schematic of where there's 3 injections. Again, I'm showing flame temperature and some arbitrary units versus engine position with, again, 0 being top dead center. We got to keep this temperature low so we don't have high NOx values, but we have to keep the end temperature high to avoid excess PM and to oxidize PM. And to ensure that we have the correct combustion phasing in overall fuels, where the auto ignition temperature may change considerably or the cetane number, we add pilot injection, and that gives us lower rates of pressure rise and control when combustion begins. So then we get the primary heat release from this main injection, and then this final injection here both increases the end temperature and also adds some momentum late in the cycle to assist in particulate mass oxidation. Again, notice that though that we're primarily retarded with respect to all these effects. And although we often tend to think, and we'll see this picture that John Deck has put together, this is really a very transient event, right? This is a very short injection period. 100 microseconds or maybe 50 microseconds. Even this event is very transient. Much of this period of time, we're not at any case where we would call it to be a steady state condition. And obviously this is another very transient event. So the whole combustion process, the whole spray process, the whole development of the combustion is inherently transient, because on top of this you have all the fluid motion, squish, reverse squish, and swirl in the cylinder happening at the same time. So that hopefully puts us in perspective of where we stand. It's a complex system where we have trade-offs of NOx, particulate, efficiency, with significant advances in the fuel system, but those advances haven't been allowed us to obtain the optimum performance efficiencies as yet. So now I'll talk briefly about what's the state of spray and combustion diagnostics and some of the parameterization work that's been done through that work in trying to help us quantify the global characteristics of diesel sprays. And this is the picture that John had showed us. It comes from John Deck and others at Sandia National Labs. But it gives us this schematic, this conceptual steady state of what a pseudo steady state view of this combusting jet would be. Again, liquid, and then a liquid vapor, finally turning all to vapor, depending upon what the conditions are of momentum flux and the kinetics of the fuel. The liquid may penetrate past where the flame liftoff area may be, or the liquid may be shorter than this. And that turns out to have a big impact on whether, on the production of soot in the system. Soot is generated generally in the internal, NOx around the peripheral. But if we take a look at some pictures, we'll see that this conceptual view, although it's helpful to understand it, is this really what we see in most applications with diesel combustion. So here's some frames from high-speed movies in a combustion facility. We're operating at densities typical of a highly boosted diesel engine, so somewhere an engine that has about 2.5 bar boost. We're operating under 3 different temperature conditions. Here we're at relatively low temperature, but again the density is the same here, and the density is the controlling factor with respect to how the momentum exchange occurs between the liquid phase and the gas phase. So we're at low temperature here, and so there's very little atomization, but what quickly happens is we create these very small particles, and we're entraining air such that it behaves much like a gas jet out here once we've created these very small diameter particles. If we were to increase the temperature as consistent with what we see in cylinder prior to combustion, though, as John alluded to, we get very short liquid penetrations. And then what we would see out here, if we were to somehow see the gas phase through some Rayleigh scattering or something, we'd see this similar gas phase cloud protruding at much the same cone angle and much the same rate as the liquid case would be. And in fact, if you were to measure them, you wouldn't be able to distinguish the two. But on top of that, at some point in the process, depending upon what the characteristics of the kinetics of the fuel are, or cetane number is, we would get auto-ignition, flame propagating around the primary mixing zone, and then flame propagating up towards the liquid portion. And this flame may propagate all the way back to where this liquid be, or there may be a standoff distance between these, depending much upon what the injector characteristics are, the hole diameter, the injection pressure, et cetera, et cetera. But, and what you're seeing here is primarily luminosity from the soot oxidation. Okay, I can stop this. So I'm just trying to illustrate here quickly that although we have this nice pretty picture of what the jet should be, it really doesn't look like that at all, right? So if we were to take laser-induced incandescence measurements of soot inside the spray, we'd see images like this. And so there's a very highly defined structure within these, and this structure is dynamic, right? So we don't see this kind of global uniform cloud of soot produced in the center of the spray. And I think that we're trying to produce evidence that we're trying to connect the near field flow, and in fact in nozzle flow, connection with the near field or primary atomization with this structure. Now we haven't gotten that far yet, but that's our goal. We're kind of moving from this end backwards, right, to try to connect essentially what's happening in the nozzle with near field or primary atomization with structure in here, and we're beginning to put some of that story together. But it's not this simple case where we have this rather uniform mixing in the center of the jet. And in fact, we have results from 2 injectors that have nearly identical nozzles in terms of diameter, L over D ratios, but have some differences in the hydrodynamic conditioning of the nozzles, and such that its rate of injection is the same. Our global spray parameterization is the same in terms of penetration of the spray, penetration of the liquid. But when we get to the measurements of soot, or actually the performance characteristics in the engine, there's a significant difference in the soot emissions from those 2 nozzles, even though the spray on its global characteristics appears to be very similar. So I'm going to back up a little bit and say, what is the state of the art in these kind of global spray characteristics? So there's a large number of people that have worked on this, but they're showing that we can, through correct analysis, conservation of momentum with this ideal mixing rate, or is essentially that we're really mixing rate limited in such that we are exchanging momentum nearly instantaneously with the gas phase and exchanging energy instantaneously with the gas phase in equilibrium. So we can compute what these should be in this momentum and energy equilibrium in terms of penetration versus time on a non-dimensional scale, accounting for all the momentum corrections or all the momentum fluxes. And similarly, if we account for the energy transport from the hot gases through vaporization of the core of the mass of the liquid, we can easily predict that, and those correlate well with these models. So everything is suggesting here that we understand the global characteristics of the spray with respect to this ideal mixing rate model, where we've essentially exchanged instantaneously the momentum of the liquid with the gas phase, and simultaneously we're and similarly with energy exchange with respect to how that controls vaporization. And vaporization here is marked by this non-dimensional liquid length as a function of this parameter in terms of this is a non-dimensional temperature. So we understand what the global characteristics are, and we're very good at measuring this, and we've done this a lot over a really wide range of conditions that go well beyond conditions you'd see in the engine today, densities 2 or 3 factors above what they're running engines today over a wide ranges of temperatures, and everything works well. And in fact, if we look at the community today, if you were to go to any of the engine OEMs, they would be using tools, CFD tools, such as John talked about, to design engines. Right? They're designing combustion chambers, developing targeting optimization for the injectors. So here you see 2 different differences in the combustion chamber. So this dark blue here outlines what the shape of the piston bowl is for 2 different configurations. Here's a reentrant bowl, and here's a chamfer bowl and just a standard reentrant bowl, 2 kind of typical combustion chambers. And through this work, they can look at essentially optimizing the air utilization. So if we optimize the air utilization, we can improve combustion performance. And looking at combustion phasing, we can kind of tell whether we're going to improve or not NOx levels. And if we look at air-fuel ratio maps, we can kind of say something about whether soot is going to be higher or lower, but soot really isn't a predictive measurement here. But there's a number of tools used, Kiva, AVL, Fire, and Converge, which is an offshoot from the work at Wisconsin. So these tools are used effectively as design tools today. But they can't predict necessarily emissions trends, and they can't tell us what the nozzle configurations can be, right? They can tell us we need this mass flow rate, and if I know what this mass flow rate is, I can tell you what this general trend is. But if I have nozzle A and nozzle B, it can't tell me anything about the details here because there's differences that we can't comprehend, nor can we model currently with this level of model. So we can understand targeting, we can understand air utilization, but we can't understand in-nozzle effects and primary atomization on the extent at which it produces soot in the cylinder, or oxidation in the soot in the cylinder. So I'm going to talk briefly next about this ECN partnership. So there's a large group of us, obviously, working in this area, including many of you in this room. But Sandia has been in a leadership area in this period of time for some area. They first established a combustion network to look at fundamental combustion work, and then recently the group there started this program to focus on engine combustion. Again, to bring the community together, to focus on the problem. And there's really three groups currently. Well, this diesel group is established. We've been meeting for over a year. We're developing a new gasoline direct injection sprays to answer the questions that John discussed with respect to those applications. And we're developing a similar, we're trying to develop a similar community on the modeling side. So it's a pretty big, a pretty good program. It's really to develop an international collaboration on both the experimental side and computational side, patterned after this turbulent non-premixed flame workshop that's been successful for a couple decades, to develop a library of experience, realizing that we all don't have the same capabilities, nor do we necessarily have the same type of facilities to do the same type of tests. So some facilities are better suited for some tests, some facilities are better suited for some tests, some people are better suited for some diagnostics than others, but to try to focus on an isolated set of conditions such that we can put as much effort in that set of conditions to give us the most amount of detail about those specific conditions, to enable further understanding of those conditions, to provide a framework for modelers to utilize this information in a comprehensive way. And so some of the people involved we're using the Bosch injectors, Argon, and their in situ work. Some OEMs, General Motors, Caterpillar, Sandia obviously is the leader of this, but a number of international institutions, IFP, CMT, Chalmers, with some people bringing on new facilities in the short term, hopefully. But if you were to go to Sandia's website, you would see the work that we did last May and the publications produced from that. Essentially, each one of these groups put together had a different responsibility in terms of beginning to develop specific data sets. And you'll find that information on the web if you just go to the Sandia website and look for ECN, you'll find the output from that workshop. And the next workshop is scheduled, I think, here in 2012 in Germany. And so if you'd like to participate in the next one, I think there's information on how you would how you'd be able to participate that in the 2012 partnership. Again, and we're encouraging modelers to begin to participate more in this, and so we're trying to develop this modeling team also. Test conditions that we're running, we really focused, all of us have really focused on one condition, which is a light-duty engine we call Spray A. So if you hear anybody talk about Spray A, this is it. It's a vaporizing, non-combusting, and combusting case at a kind of medium density, a relatively low gas temperature. This corresponds to 60 bar atmospheric pressure, a single hole nozzle with 1500 bar injection pressure with endodecane as the fuel. There's a whole sequence of tests that we're scheduled to run through. Our work at Michigan Tech tends to focus on a different engine technology, although there's some similarities. So much of the work that we report more recently are with a different injector, but conditions are similar, and I'll show you how those match. Within this group, there's really two primary facilities that are used to do this work in. We're not using optical engines. We're using some kind of combustion vessel or combustion rig. There's two primary mechanisms to get the temperatures needed for representing the temperature pressures in an engine after compression. One is a flow rig that's design comes out of Aachen. The second one is this premix chamber, pre-burn chamber that work goes back a couple decades from Sandia. This is the type of facility that we run at Michigan Tech. But essentially, we have a lean dilute mixture here of hydrogen, acetylene, oxygen, and nitrogen, and we can tailor this such that we can tailor the amount of oxygen post-combustion. This goes through a lean premix burn. There's fans in the system up here to ensure that after the premix burn, we're at uniform temperature and uniform composition. Then after a significant cool down period with respect to the time of the diesel, we're tracking this position. At this case, we're at a constant pressure, constant density condition. So knowing pressure, we know temperature, and we can inject at the temperature that we want to inject in. And then the diesel injection occurs. And depending on whether we have oxygen in the environment or not, we can study vaporization or combusting. Obviously, we can do low temperature tests too. And then this work is repeated over the conditions that we need to do. One advantage of these systems is we can get relatively high temperatures prior to combustion, and in particular, one of the vessel designs, including the Sandia and the one at Michigan Tech, gives us a relatively high ambient pressures. We can study pressures up to 350 bar ambient pressures. If we were to look at the conditions in terms of ambient temperature and pressure, there's still one other axis that we can control, which is the amount of oxygens in the constituents. So by changing this premix burn, we can change the amount of oxygen in the post products of this premix burn, which represent the composition at the time of diesel injection. But all three of these can be independently changed, essentially test to test, although it takes a little bit of time to generate new mixtures here. If we look at kind of where engine technologies exist, here's what a naturally aspirated curve. So we just follow a polytropic compression for a compression ratio 4 to compression ratio 24 engine, or if we follow a highly boosted engine, so a 10 bar boosted engine, noting that most engines are currently not boosted only to about 2 or 3 atmospheres, so a current engine would fall in here. We could attain really all the conditions in terms of temperature, pressure, and concentrations that we would expect to see in modern engines or really any advanced engine technology. And if we look at how the conditions fall, here's the spray A condition. It's a lightly boosted low temperature case. There's a low temperature case in the ECN, a low temperature, high dilution case, and then there's a high load case in that set of tests can do. So these are some of the test conditions that are outlined in the ECN network work. Just in comparison, if we look at previous work, so I showed you those correlations for liftoff and spray penetration. Those were typically done as a function of constant density with other parameters changing, and we had run densities considerably even lower than this. So we would run the tests where we're holding density constant, 64. We even ran some tests, I think, up to 128, so density is way out here. So our conditions that we've done these global parameterization has really covered the entire range of which we would expect engine operation to occur, even to ranges that would be well above which we would see in a modern day engine. And these are two of our common points here. One that's a naturally aspirated engine modeled after a kind of a medium duty, and then this density of 34.6 is essentially a full load condition on a medium duty engine. Right, so through that partnership, we're hoping to gain more insight by collaborating together and bringing together the expertise, not only on the experimental side, but then through participation of the modeling, trying to understand better the effects that we don't understand. So I'm going to talk briefly about fuels. Both in the aerospace and in now more recently in the IC engine community and diesel community, there's been a focus on generating fuels for study that more realistically characterize those of diesel fuel, realizing that it's difficult to study diesel fuel because it has so many constituents. What we want to do is come up with a model fuel that has the right characteristics. So what are the right characteristics? I don't know. Maybe we don't even know what the right characteristics are. But certainly there's chemical structure, there's the thermophysical properties, the thermodynamic properties. Which one of these are important? And so several models have been proposed, but these models mostly focus on developing detailed combustion kinetics models, not necessarily models to match the thermophysical and thermodynamic properties. And so I think there's still a great amount of study needed on some of these proposed surrogates, because really there's been very little work in these surrogates under realistic diesel engine conditions to see what liftoff looks like, what soot production looks like, what the flame liftoff looks like. And some of these surrogates that have been proposed are pretty high cost that really are a hindrance to do spray combustion studies, nonetheless trying to run engines on these where we're paying thousands of dollars an ounce for these fuels. So there's a whole number of proposed components that we could look at. There are some studies by Ling et al. Recently at looking at some multi-component surrogates. So I think there's an entire avenue here of what are the appropriate surrogates, or what's the appropriate surrogates that we should be using for these studies with respect to the spray and vaporization studies, whereas most of the work, again, has been focused more on the chemical kinetics activities rather than the spray and atomization work. That are going to control the things like soot production. We just don't have the data there yet to say what do we need to match. We have begun studies, though, using equation of states of multi-component surrogates to try to understand saturation pressure, temperatures, enthalpies. Again, noting that our global spray parameters are primarily mixing controlled, we can rely on our thermodynamic properties and getting good analysis of real gas and real fluid characteristics through equations of state, including the charged gases. We can then begin to improve our correlations, or at least understand how these component mixtures will affect things like our liquid length, and then how our models correlate to those using different surrogate fuels. Again, more work here is needed. We're just starting this work trying to understand what are the surrogates we should use, what are the surrogate characteristics we need to match, under what conditions do they need to match, and how important are they in production of both the global characteristics like liquid length and the structure of soot formation and other things. So I think there's a large avenue open in fuels. And then finally, I'll finish with this. We kind of talked about this briefly to begin with. We have this conceptual model of what a diesel spray looks like, but it's much more complicated than that if we start to dig down and look at its internal structure. So if we take high-speed images of just the near liquid region, and so now we're just seeing an 8-hole spray. We've zoomed in quite a bit. We're at 1,000 degrees Kelvin, this high load condition, peak injection pressure, 67,000 frames per second. And if we look at the structure of the liquid spray, it's not this constant value. There's some kind of structure in this. There's structure in both this, and there's differences in its liquid penetration that has significant dynamics. So what's controlling that? Where does this come from? Does this come from in-nozzle artifacts? Does it come from near-field primary atomization? I don't think we're ready to say yet, but this is what we're trying to understand now, is why does this occur and how does this affect downstream? So again, I think what we need to do is understand what the nozzle internals are doing, understand what the near field primary atomization is doing, or how that may be changing the air entrainment or gas entrainment to affect liquid length, but then what's going to happen downstream to variations in air-fuel ratio and mixture dynamically, and how does that change the structure that we see in soot formation and global spray formation. And so we can characterize the liquid length as a function of temperature. We observe this scatter because of this dynamic fluctuation. We began to quantify that statistically. So if we look at just kind of this steady state portion, we can look at the liquid length or its difference from the mean and what does that look like statistically. We can begin to do some kind of frequency analysis to look at what are the dynamics in the system. So we can look at the frequency of essentially the length of this. So if we can look at this in terms of the power spectral density in the length unit squared in terms of its frequency content, and identify if there's structure, repeated structure in this. And then finally, we can look at the internal structure itself and look at spatial frequencies within this to see if there's certain spatial characteristics. Our goal is to take this through all stages for both the near field flow, the liquid portion, the gas phase, and then finally to the soot to try to understand how this connects into the performance of the injector with respect to its combustion and emissions performance. So in summary, I think we have a good handle of the global characteristics of diesel spray combustion. Our correlations work well. If you tell me the orifice diameter, the injection pressure, et cetera, I can pretty much tell you what the fuel penetration will be. I can give you a good idea of what the liquid penetration will be. With addition of CFD models, we can optimize engines in terms of their ability to target or to optimize spray targeting, to optimize chamber designs, but we aren't able to predict emissions. What I think some of the needs are, we need to think about what are the fuels, the surrogate fuels we need to use, what are the characteristics we need to match. We'd like to get some fuels that we could actually match to and ensure that we can validate against emissions in an engine, because that's really the goal here, is to produce results that can take us all the way to fundamental spray characteristics, all the way to engine performance factors. I don't think we understand well enough the impact of nozzles or near spray development and their impact on downstream vaporization, combustion, and soot. And I think there's a large amount of dynamics or structure within the spray that itself that we need to understand if we're going to be able to do to better understand what the effects are of near field and in injector and nozzle flow dependencies. And I guess I'll finish with that. I'd say there is a lot of work to do in GDI engines, so we have a panel meeting on this tomorrow, but there is a lot to work in GDI engines. And I think we see much more differences in the global characteristics in gasoline direct injection engines. For instance, as we change the fuel composition from, here's some heptane to ethanol to an E85 mixture. And so we see very different characteristics in even its global structure as we change things with respect to ambient pressure. So there's certainly a large amount of work we need to do in that study. But today I tried to give you a little bit outline of what it looks like still. There may be a little bit of work, or maybe we can still do a little bit of work in diesel sprays to try to understand what some of the remaining issues are there.
Thank you, Professor Naber. We can have two questions.
Thank you. You were referring to surrogates, and if I got it right, did you actually mention that there isn't any consensus in the community with respect to how we should actually arrive at the surrogate, or there are no ways of arriving at the surrogate?
Well, I think there's teams working on multiple surrogate models. that have been very focused on developing large-scale kinetics models for these, right? And there are different opinions in those, right? There are differing opinions in how many chemical classes we need to match. You know what?
I mean, you have Princeton, they have Muri, the group which lists the criteria that you can actually
You have the Princeton group working on the
then they
on
have
their
the
group.
and you have the Model Fuel Consortium, Professor Santoro, Wang, reaction design and others. So are you referring to the fact that, I mean, they
But
do
it-
take into account the thermodynamic.
But if you look at their work, you show me where they've done any soot estimation of in cylinder or any work where they've done soot measurements in cylinder where there's surrogates. They haven't, right? They've done some soot, some basic soot characterization work,
Yeah.
but they're not under the conditions at which we do diesel combustion at. Low temperatures, maximum. They're not under conditions at which we would expect that diesel combustion occurs, right? So there's very little work with those surrogates under the conditions of diesel fuel spray and combustion.
Okay.
So if there are no further questions, let's thank once again Professor Naber.